All right, so today, or this time, whichever it is, we are going to cover Unit 8A. So this is the difference between exponential growth and linear growth. All right, so kind of for a first example, we are going to talk about two towns. One is Straight Town, one called Power Town. Now, Straight Town has an initial population of 10,000 people, and it grows at 500 people per year. So 10,500 after 1 year, 11,000 after 2 years, 11,500 after 3 years, so on and so forth. Okay. Power Town grows at 5% per year. So after 1 year, 5% of 10,000 is 500. 5% of that, though, is 525. So now we're at 11,025. 5% of that is 551. Okay, and so on and so forth. So here is the graphs of the two towns. Okay. Now, Straight Town is known as linear growth. It is the same amount every single year. Okay, and that growth will make a line. Power Town is based on a percentage, and that means that each year, while the percentage is the same, the total number of people growing, in this case, is going to change. Okay, it's going to get more and more each year because the bigger the number, the bigger the number of people that grow to make the same percent. And so what you see is at about 14 years, a little before 15, is what's known as the doubling time period. So we've gone from 10,000 to 20,000. Now it takes the same amount of time to double. So another 14 years, or about 28 years, we've doubled again. But instead of growing 10,000 people, we've now grown 20,000 people. And then after 14 more years, we're going to double again, but it's going to take 40,000 people now to double. So while the doubling period stays the same, the amount of people that need to double increases from 10,000 to 20,000 to 40,000. Okay, so linear growth is when the quantity stays the same by the absolute amount. Exponential growth is a percent. So when you're doing these, you need to determine whether it says, or whether it's a linear growth or an exponential growth. If it's growing by the same amount every year, it is linear. If it's a percent, it is exponential. All right, so a couple more examples. Couple ways you can do these. One way is you can simply just kind of make a chart and increase it by years. Totally fine. It works. If you're trying to find something, 10 to 20 years out, it can be a little bit of a challenge, but you can do it. If you would like to make an equation, you can. For linear growth, you can do the amount plus the change times the number of years or days or whatever time period you are. If it is exponential, it's the amount times 1 plus the rate change. Remember, it's a percentage. And then you're going to close the parentheses and raise it to the power. Or you can run it out if you would like to do it as well. Now, if it is decaying, that means it is decreasing. Then it's going to be a subtract, but you would realize that you are decreasing, so it's a minus sign. All right, so let's take a look at some of these. All right, A, we got Wilson High School. We are increasing 50 students per year. Linear or exponential? Well, it's the same amount every year, so it's linear. Population was 754 years ago. What do you want to know? We want to know what it is today. So 750 plus 50 times 4 is 950 students. All right, for B, the price of milk has been raising 3% per year. All right, so we're dealing with a percent, so that would be exponential. If you would like to, you can. So we're going to take 4 times 0.03, gives us 0.12. So in other words, it rose by 12 cents over the last year, and that gives us $4.12 now. Okay, you could have plugged it in and gone 4 times 1 plus 0.03 raised to the first, and you would have gotten the same thing. I just did it that way so you can kind of see the breakdown. All right. C, we got tax laws. We're depreciating our equipment $200 per year. So it's the same amount every year. It's going to make it linear. Started with $1,000. It's been 3 years. So 1,000 minus 200, because we are losing that money, times 3 means your value is $400 today. All right, memory capability is doubling every 2 years. So we started out with 16. We are doubling, that's a percentage. So it's exponential. So we could go 16 times 2 to the 3, third power, and it's 128. Now it's not 6 because it takes 2 years to double. So it's 3 doubling cycles. And if you wanted to, you could have worked it out. 12, 2 years later, 32, 2 years later after that, 64, 2 years after that would be 128. All right, we have a high-def TV, loses 25% per year, so 25% means exponential. Started at 1,000, so we're going to go 1,000 times 1 minus 0.25. There's our percentage, and we're subtracting it because we're losing value. Raised to the second power, and our TV's new value is $562.50. All right, we got Foxtrots. Math teacher is offering to assign 1 second of homework the first week of school, 2 seconds for the second week, 4 seconds for the third week, so on and so forth. Yeah, the question is, if the amount of homework doubles every week, is this something you agree to over 36 weeks of school? She's a little bit worried. Mr. Thompson is evil. That is something you should be worried about. You can figure out how much work she would have after 30, 31, 32 weeks. All right. So we have a 1938 comic book that was sold at auction in 2005. The owner bought it for $55 in 1980. What is the value if it increases by 2.8% per year? So 55 was the initial amount. And then we're going to go parentheses 1 plus 0.028. That would be our 2.8% change to a decimal, raised to the number of years. Now in this case, the 1938 doesn't really mean a whole lot. The owner had it for 25 years, from 1980 to 2005. So we're going to put a 25 in for Y, and they would have sold for approximately $109.70. And we have a guy here that's eating twice as many vegetables as he used to, but 2 times nothing is still nothing. And we have a teacher that gave 100 questions on exponents. It's a math class, but is that an abuse of power? All right. So the story goes, kind of a couple examples of what doubling does, or what exponential does. The story goes that chess was invented, and the king absolutely loved the game. So he told the inventor, ask for anything you want, and I'll give it to you. So the inventor says, I want 1 grain of wheat on the first square of the chessboard, 2 grains of wheat on the second, 4 on the third, 8 on the fourth, so on and so forth. And the king agreed, thinking, hey, it's going to be an easy payoff. Much like our Foxtrot student, thinking that 1 second of homework, 2 seconds of homework, 4 seconds of homework may or may not be that big a deal. But as you look at it, 5 is not too bad. You get 31 pieces of grain and so on and so forth. However, by the time you get to the last grain, that would be 2 to the 64th power minus 1. And that would be 1.8 times 10 to the 19th, or 18 billion billion. That is more grains of wheat than have ever been harvested since the world began. So the king couldn't pay the inventor, and according to legend, had him beheaded. So be careful what you ask for. Along the same lines, you meet a leprechaun. And he gives you a penny and disappears. You take it home, put the penny under your pillow. The next morning you have 2 pennies. The morning after that you have 4. The morning after that you have 8. Then you have 16, and then you have 32, and then you have 64, and then you have $1.28. So if that continues, okay, after a month, okay, you have $10.7 million. If it keeps going, by the time you hit 51 days, you will have $22.5 trillion, which at the time this was written would pay off the national debt. Unfortunately, that is no longer the case. You would have to go to 52 days when you had $45 trillion before you could pay off the national debt. But that's what doubling is. So you can go back and see if our Foxtrot student should sign or agree to the second of homework a day, or second homework of a week doubled. Okay. So most things don't double that quickly, but it gives you a pretty good indication of what it is. All right, so that is your exponential growth, your linear growth. Once again, if it's a set amount every time, then it is linear. If it's a percentage change, then it is exponential.